So, as Paul said, I've been doing this for a while now. When I was a graduate student here, I was working in MEMS, trying to make micro robots, and got my PhD in '92 and went down to UCLA and started teaching there to continue to work on micro robots. And one of the first things I did was go to a workshop at RAND where we talked about the convergence of MEMS technology making microsensors and Moore's Law and the communication revolution that was going on at that time. And out of that workshop in 1992, 15 years ago, came this idea that since all three of those things, the sensing, computation, and communication, were all following some kind of exponential curves down to zero size, power, and cost, that a wireless sensor node would similarly be following those curves down. Because the last piece that you need is the battery, and the power demands on the battery are getting smaller every year, so the whole thing was getting smaller and cheaper. So that was really that's where the ideas for smart dust appeared, and I coined the phrase 4 years later, and that's probably the most important thing that I did in the field, is to give people a label for it that they could talk about, because that people sort of got that. Anyway, got to Berkeley in '97 and wrote a proposal of the same name, Smart Dust, with Bernard Bozer and Joe Kahn, and we had a lot of fun doing that. And then things looked really good for a while, and then it seemed like everything kind of slowed down. And we had all this interest in commercialization and all these markets that everybody thought were going to take off, and it didn't. And so I'm going to talk a little bit about what happened there and what the solutions are to those problems, and why things really are finally starting to take off now, and then where we're headed next in the university. And this is sort of a joint professor hat, CTO of Dust Networks hat talk. So I'll try not to be too commercial. But back in '97, the first proposal that we wrote on the smart dust topic with me and Joe Kahn was for $25K of university funding to work on autonomous microsensor networks using optical communication links. And we built some fun little devices. So like this guy right here had a microprocessor, and it was a little weather sensor. It had light, temperature, barometric pressure, and humidity, and then the front end of a laser pointer that we cut off and wired into the microprocessor. And I had my grad students go over to San Francisco up at Coit Tower, and they pointed that laser back across the bay to my office, where I had a little camera, and actually some undergrads wrote the software that grabbed successive frames from the camera and looked for the little red dot winking on and off. And we did laser communication across the bay, 26 kilometers, with the weather station data, and that worked. And we went on and miniaturized the optical communication stuff with corner cubes and things like that, and ended up making these little rice grain-sized wireless sensor nodes. And that was a lot of fun. Did some very nice research in there. But the thing that got people excited was when we started building the off-the-shelf nodes. So I had Seth Holler, one of my master's students from mechanical engineering, interestingly, build this little guy. That was the first node that had a radio and a microprocessor on it. It also had a half a dozen sensors. And we made 10 of those and showed that we could make multi-hop networks, that we could do some localization based on who was talking to whom in the network, see where people were. And that was Seth's master's thesis back in '99, I think, or 2000, something like that. And that got David Culler interested, and David and I had a grad student, Jason Hill, who wrote the TinyOS operating system, and then that just took off. And David ran with that, and all sorts of neat things happened over the next few years. And in 2001, we did all these little demos. So this is 6 years ago now, actually more than 6 for most of them. 800 nodes forming multi-hop mesh networks at the Intel Developers Forum, and gives you a sense of the size of the nodes back then. Some nice work Steve Glazer and his students did instrumenting the shaker table out at Richmond and measuring things. Dropped motes off a little airplane and detected vehicles in the desert for military application. And then the one that really kind of kicked off the commercialization side, we put in 50 light and temperature sensors into the 4th floor of Corey Hall in an afternoon at a cost of something like $100 per. And at the same time, Honeywell was going in and redoing our HVAC system and charging us $800 per node that they put in, plus putting ugly conduit and everything else around the walls. So that's when people started to lean on me to commercialize the technology. And also when people started talking seriously about this being a revolutionary technology for a new industry. And the reason is this, that very, very roughly, the cost of computing power is going down exponentially in the same way that the power that you have on your desktop is going up exponentially. I mean, we're hitting limits there, but that's a separate talk. And the MEMS technology going into the sensors, very roughly, is following similar kinds of curves. They're not Moore's law, it's not perfect exponentials, but absolutely things are getting cheaper and higher performance every year. The problem is, so as far as wired sensor networks are concerned, these are great things. And we're surrounded by wired sensor networks. This is a neat room to work in to talk about wired sensor networks, because if you look around the walls, they're filled with conduit, right? And if you look, almost all that conduit is going to sensors. There's fire sensors over there, there's a fire sensor over here, there's a temperature sensor back there, there's a couple of cameras, those are arguably sensors, there's light switches, you can call them sensors, there's a passive IR sensor to see whether people are in the room, there's sensors all over here, they're all wired into networks. This is a huge, huge industry. And the problem is that even though the sensors and the computing power are getting cheaper, the cost of conduit is not. And the installed cost of conduit is really not when you figure in labor. And so the thing that's exciting about this technology is that we have the potential, by using wireless mesh networking, to get off of labor and material curves for the installation and get onto curves that look more like information technology kinds of things. Now, there's a whole other set of applications that just aren't possible with conduit and wire, and those are exciting as well. But for the majority of the commercial interest in the near term, it's this idea of reducing the installation cost. So this, everybody's excited about this. There are industry analysts who are paid to predict where the industry is going to go. And here's from a report that was done in 2003, shows that the red line is wireless sensor networks, and that by 2007, they are supposed to be eclipsing cell phone handsets in volume shipments. And that clearly did not happen. That's kind of what industry analysts do. They like to draw exponentials, and they just keep pushing them out a little bit. Zigbee Industrial Alliance was formed to commercialize this stuff. Everybody was very excited about it. They worked absolutely gangbusters to get a standard out there, any standard out as fast as possible, because everybody felt like this was going to be a land grab and it was just going to take off, and all that mattered was time to market. You just got to get a standard and get it out there, and things will happen. And so Zigbee 2004 came out after the IEEE published a radio standard in 2003. 802.15.4 is the IEEE radio standard. And then nothing happened. We all sort of sat around. I started my company in July of 2002. There were a whole bunch of wireless sensor network startups in 2002, 2003. And we're all sitting around kind of tapping our feet waiting to be millionaires. And not much happened. So a couple years later, Zigbee 2006 came out. Not compatible with Zigbee 2004. It was not backward compatible. No one cared. There were no Zigbee products introduced in that 2-year period because the technology didn't do what people wanted. And they just recently scrapped that and introduced Zigbee Pro in 2007. And it at least is backward compatible with Zigbee 2006. But of course, and as I'll show you, I think that's a huge mistake. All of the Zigbee standards are single channel 802.15.4 networks. And as I'll show you, it's a very dangerous thing to build a single channel narrowband network in an unlicensed spectrum, the 2.4 gigahertz spectrum that you share with Wi-Fi and cordless phones and all sorts of other ugly things. So the good news is that I think all of these markets are real. I think, and more, right? There's tons of other things that aren't on here, but all of this is real. Agriculture should be on here. I don't think that's up there. Defense should be on there. I don't think that's up there. I do think that we are going to end up having an impact on all these different fields. It's just we needed to get the right technology to do it. So around 2005, people started asking, well, why isn't this taking off? Venture capitalists have invested $100 million or maybe $200 million at that point. What's preventing you from adopting wireless sensor networks? So in 2005, OnWorld did this study, and the number one reason was reliability. People had a history of being burned by wireless. Ever since Marconi, people have tried to put in wireless sensors, and it turns out it's a painful thing to do, that it's really tough to guarantee reliability. And this, I want to make sure I'm clear about what reliability is. There's reliability for computers like we think of, for Microsoft Windows. And people say, oh, Microsoft Windows is horrible because it blue screens on me every now and then. And one of the reasons why wireless sensor network software isn't reliable is because it's, people haven't worked hard enough on that. That's one kind of reliability. The other one is protocol reliability. Given the the challenges of the RF environment that I've got and the radios that I've got to work with, even if I assume that my little computers are going to stay up all the time, am I going to get my data through? And that's the reliability that I really care about. If you spend enough time on the software, eventually there's not enough lines of code in these things to screw it up that badly. Eventually, you can fix the code. But if the algorithm that you're running is wrong, if the underlying assumptions about how to communicate is wrong, you'll never get the reliability you need. So that's the single biggest challenge. And that was, out in an industry that was absolutely, I would say it was skewed even more toward reliability. If you didn't solve that one, nobody would even talk to you about anything else. You can give it to them for free, zero power, didn't matter. They weren't going to use it. So standards, ease of use, power consumption's up there. People wanted battery-powered networks, development cycles. And then, of course, interestingly enough, the thing that I started off as the most interesting problem to work on academically, totally unimportant. Nobody cares about node size. There are very few applications where it matters. Medical is one of them. If you're a patient and you want to have wireless sensors on you, you'd rather not have something that's got a couple of C-cell batteries hanging off of each one of the electrodes that's on your EKG or whatever it is. So started Desk Networks in middle of 2002. The founding team, between us, I think we had 13 degrees from Berkeley between the five of us. So a bunch of Berkeley guys, and reliability and power consumption were sort of number one, 2, 3, 4, and 5 on the list. And to do that, technologically, we had to develop a new protocol, what we call TSMP, or the Time Synchronized Mesh Protocol, to get very high reliability and low power consumption. And so I'm going to spend some time talking to you about TSMP, partly because I think it's the only solution that's out there right now that works, and maybe more importantly because it is being adopted by a whole bunch of standards bodies now. And so, like it or not, whether I'm right that it's the right way to do it, it's going to be around for a while, and it's what people are going to be running into. So let's say I've got two nodes and they want to communicate, and we'll assume that they can be time synchronized. We don't know how yet, but somehow magically they have a shared sense of time accurate to within about a millisecond. And in one of the standards, that is, in fact, it. Plus minus 1 millisecond is the accuracy of the clocks that we maintain. So if A expects B to send a packet that starts at a particular time, it knows there may be as much as a millisecond difference in its time base relative to B, so it better wake up a little bit early. So it wakes up early, and it knows it better stay awake a little bit longer. And if after that 2 millisecond interval, it hasn't heard the beginning of the packet from B, it knows it's not coming. Either B didn't have anything to say, or the signal was jammed by a Wi-Fi transmission, or multipath interference in the environment just made it so that the signal from B just couldn't get through, and there was zero received power, and that's a real challenge for these little radios. But if we assume that B did have something to say and it did start transmitting, then A leaves its transmitter on and records the transmission. It also records exactly when that transmission started. And so now I know, right, A knows when it expected the packet to start. It knows when B actually sent it. It knows that B tried to send it at exactly the right time in its time frame. So now it knows the difference between its clock, A's clock, and B's clock. And it turns around, sends back an acknowledgement, and says, I got your packet. Everything checks out OK. And by the way, you were 0.6 milliseconds late. So now you have timing information that's gone in both directions, and you can use some either simple or complicated algorithm to figure out how to adjust the clocks on the two different nodes. And it turns out you can propagate time accurate to around 50 microseconds relatively easily over an entire network, multi-hop network, in this way without spending too much power on it. And now A has the packet, B deletes the packet, and that's it. And we move on from there. So what does it cost to send that packet? If we plot the current that the mote is pulling out of the battery versus time, and look at the pieces of it, there's some power associated with starting the thing up, transmitting the packet, turning the radio around into receive mode, and then actually receiving the acknowledgement. And if you integrate current versus time, you get charge, right? That's the fundamental quantity that the battery has in it that you're trying to get out. And so the area of each one of those areas tells you how much charge you're pulling out in coulombs. And for a radio 4 years ago, the integral under that curve was around 300 microcoulombs. That's gone down by roughly a factor of 5 with today's radios. So now I know how many microcoulombs it takes. How long is this whole thing? You know, how often can I do this? You know, there's a bunch of stuff that has to happen inside there. I think I actually swapped A and B here, unfortunately. I've got A transmitting and B receiving, sorry. So there's some time for the radios to start up. There's this guard time that I've got. Maybe A is maximally late in its transmission, so I really have to waste that whole guard time. Then when B gets the packet, it has to check some crypto stuff, make sure all the bits got through correctly, and then it's got to do some crypto on the acknowledgement that it sends back, because you don't want anybody to be able to come in and spoof your network. You've got to have crypto in both directions. Everybody wants their communication to be secure and unspoofable and everything else. And then you've got to transmit the ACK. And when you're all done and you go through all the numbers with the radios that we've got today, and you add that up, you find that it's about 9 milliseconds, about half of which is spent actually sending the packet itself. So in the HART standard, we picked 10 milliseconds as the time slot. So you get to do this up to 100 times per second between modes, or send 100 packets per second if you want to. So I can figure out now, and I do the same kind of measurement and look at how much it costs me to receive a packet. And now I can figure out sort of the cost of the fundamental cost of delivering reliable, secure packets in a network. I add up all the times I have to transmit and all the times I have to receive and divide that by the amount of time that I'm doing that in, and I come up with my current that I'm pulling out of the battery. And so if I take some typical numbers, I'm sending and receiving once a second, and I've got the charges associated with doing that, then I get something in the 10 or tens of microamps range. And that's a great number. That number is consistent with battery lifetimes measured in years to decades, depending upon what size battery you use. And so it's a question. So that's kind of fundamental. Those are the things I have to do. Now, how much do I have to add on top of that in order to survive? Well, I can't always be guaranteed that my packet is going to get through, so I'd better schedule some extra communication slots in there in case I get jammed or what have you. And what are those going to cost me? Well, those are places where I wake up and I listen, but I don't actually have a packet to receive. And so if I look at that, there's a wake-up period and then a listen period, and then I don't hear a packet, so I go right back to sleep again. And again, 4 years ago, that was something like 70 microcoulombs. Today, that's substantially lower than that, 3 to 5 times lower than that today. And so now A can wake up and listen repeatedly. And each time it wakes up, by the way, right, A and B are time synchronized. They can use their shared sense of time to hop randomly around in the frequency band. So if there's a big, loud Wi-Fi or cordless phone somewhere in there that's jamming their communications, they can just hop around it. And they can use their time and their what they know about their partner and when their partner is going to talk to choose a channel to use. And so you wouldn't actually do them linearly, but pseudo-randomly hop inside the band. So A wakes up, and each time it doesn't hear anything. Maybe B didn't have something to say. Maybe it was jammed. We don't know. But at some point, B does actually do the transmission. A sends back the acknowledgement. The packet now belongs to A instead of B, and we go back to listening and waiting to see if B has something else to say. So those extra listens cost me something, right? I had to pay some charge for them, but that's a relatively small amount of charge, and so depending upon, if I wanted to listen once a second, maybe that's an extra 20 microamps. I'm listening 10 times more often than I expect to have packets. And maybe I do that to increase my reliability, so I have lots more opportunities, or I do it to decrease latency. But that costs me some power. So and then I want to do multi-hop communication, because these radios can't go all that far, 100 meters roughly. So I string these things together, and I put a collection of these links into what's called a superframe. And that superframe repeats in time so that I can pass messages from mode B to mode A to a gateway and so on. So that's sort of it. There's really not much more to what I spent 5 years and approximately $40 million of other people's money developing. Keep the modes time synchronized, channel hop, and don't wake up unless you have to. And then it's all just kind of engineering details of implementing all that. But it does end up being important. You get tremendous reliability out of this frequency diversity. You avoid both interference from other things, and you avoid this multi-path fading problem where you get reflections off of things and they can cancel out your communication. But they can't do it across the band. They only do it in fairly narrow areas. So you get spatial diversity out of it because you can schedule these links however you want. Temporal diversity, I keep trying until I actually get a secure acknowledgement back that says that somebody else has got my packet. And for power, right, I schedule when my radio is going to be on. It's not on unless I have some purpose for it being on. It's really easy to duty cycle a radio. Just turn it off. The challenge is knowing exactly when to turn it back on again and actually be able to do something useful with it. So a little more detail. So a link connects two nodes. It has a time slot and a channel offset that it uses. You collect multiple links into graphs. And this came out of just years of spending time at whiteboards with people with neat ideas, right? The first thing somebody does when they have an idea about an application is they go to the board and they start drawing dots on it with arrows connecting them and saying, here's how I want my data to flow this way. And then maybe I've got another one and I want it to flow down that way. And there's some handheld that comes in and they draw graphs. And they say, here's how I'm expecting the data to flow in the network. So we implemented our stuff around the idea of graphs. Graphs have different numbers or colors, and so packets flow on graphs independently. And they're sort of independent in terms of how often the links are used and what power consumption they are, how much data they can handle, the latency, and so on. So quality of service is bound to graphs in our way of doing things, which is sort of nice because it turns out, independently, I didn't know anything about networking when I started doing this, there's a lot of similarities to ATM and tag switching that Cisco uses, MPLS, and flow labels. And there's a new internet protocol called IPv6, the next generation of IP. They cleaned out a bunch of stuff out of the IPv4 header, which is what all our computers use on the internet today. The one thing that they added was a flow label, and this idea that you have packets flowing along an identified graph. And so that's sort of fun that there's, and this is a path we're going down to standardize this, is to try to take the way we do graph-based flow in a network and bring that into the ITF and IPv6. So you get to draw pretty colored graphs, and you map the links between nodes, end up with a time and channel offset, and you fill in this little matrix that's time slots on one axis, and this sort of repeats in chunks, and then which channel you're going to use on the other axis. You get 16 different channels to choose from, so you got a lot to work with. And so here's a picture where I've got 16 channels and 25 time slots, so that's 250 milliseconds. So this thing will repeat 4 times a second. And you can think about how you start scheduling multi-hop communication by just plunking in link by link by link, one after the other, and you can have that repeat after 5 slots or 25 or 250 or whatever you want. And you can easily then allocate the resources you need to your application and have a good estimate of how much charge it's going to cost you, what your power consumption is going to be. So it's a nice, it's statistical because you don't know what kind of interference you're going to have, but at least it's well modeled and nicely algorithmic in that sense. And there's lots of ways to fill in these things so that you can do things faster. All sorts of cleverness can be done when you've got this kind of flexibility. And performance limits, blah, blah, blah. So some real examples. This is a picture some of you probably seen before. This is a deployment in a printing facility on the west side of Berkeley. I'll show you a picture of it in a minute. It's a 3-floor concrete and steel building with lots of heavy machinery in it. And we put 50 motes in there. And one of them is the gateway. So this guy right there is plugged in. He's got an Ethernet port on him. And he manages the network. And then all these 50 motes report back to him. And you can see they report over a multi-hop network. And each one generates 1 packet every 40 seconds. So there's about approximately just over 100,000 packets per day gets generated in this network. And there's 2 important things that we bookkeep in this network that I'm going to spend some time talking about. One of them is the path stability, which is, so each one of these little links we look at as a separate path. And we bookkeep, this guy, once every 15 minutes, he reports in, I sent 23 packets on this path and 67 packets on that path. And these guys report how many of them they received. This guy reports how many of them were acknowledged. All this information goes back to the manager. And so the manager can get a sense of what the path stability is of all those different paths. So up to 100%. If they all go through, 100%. If none of them go through, 0%. So, and in these networks, it's very common, if you've played around with moats, that they run at around 90% stability. It depends upon how much interference you have, what kind of environment you're in, and so on. But roughly 9 out of 10 packets get through. But what the customer wants, or the end user wants, or the application developer wants, is they want the packets. They don't care about 90%. I want all my packets to pop out of this Ethernet port, right? That's why I put the network in, to get the data. If I wanted only 90% of the data, I would turn the knob down and only have them generate data 90% as often. So you want to bookkeep both of those and keep track of those. And so here's some data that's 2 years old now, over a period of a week. And here we show path stability averaged over the entire network over all the channels and everything else. And you see it's 80 to 90, 93%, something like that, maximum. And if you think about if this guy with 90% probability gets his packet there, and with 90% probability it gets there, and with 90% probability, you add up 7 hops for the furthest guy away, and pretty soon you end up with very few packets ending up getting through. But if you do retries until you get it through, if you change channels, if you use spatial diversity and try your different friends, it turns out that you can take that unreliable path and turn it into a very reliable data channel. And so here's, on the last day of this particular data set, we lost 3 packets, lost 2 packets, lost 1 packet, and there's 4 days where I didn't lose any packets. So averaged over the whole week, we had 5 nines reliability. And that's at just this sort of network MAC layer in the protocol stack. You can wrap at an application layer. You can wrap more reliability around that if you want, and wait until you get your packet acknowledged end to end before you delete it. But working with something that gives you 5 nines reliability makes that kind of thing much, much easier to do. So this is the place, this printing facility on the west side of Berkeley, and there are moats distributed around inside of here. It's sort of a typical nasty RF environment. And I don't know why, but when we did this deployment, we didn't even cover the moats up, didn't put their cases on. But here you can see, so here's a couple of AA batteries. There's the actual moat itself and the little cord coming off of the antenna, and there's the little antenna. So that's what they're sort of out there in the real world. And here's a picture of the Pathloss. So this is, at the very top of this is receiving 10 microwatts, 1 microwatt, 1 nanowatt, 1 picowatt down here. So these radios are capable of receiving signals that are down at around 1 picowatt of signal strength. And the received signal versus distance. You hear people talk about using the received signal strength as an estimate for range, or a surrogate for range estimate in order to do localization. It's pretty tough. If I tell you that I just got a packet with minus 90 dB of signal strength, I'm on this line down here, what's my range? Well, it's somewhere between 0 and 250 feet, and I don't really know where it is in between there. So this is real world. The real world does not look like your freshman physics book that tells you that fields and waves propagate as 1 over r squared. The real world in RF land looks really ugly like this. So now if we look, with 15-minute granularity over a 26-week period for this network, and look at the path stability that we got, like I said, it's this is a newer network. So the last one I showed you was 2 years old. This is about 6 months old. Path stability around 90% over the 26 days, averaged over the whole network, and then you can see the red line is averaged an average of all those points. And you can start to see some periodicity in here. This is sort of day and night and days of the week sort of stuff that we'll see more of in a second. Here it is broken down by channel now. So again, I'm still looking at 26 days worth of data. I'm looking at the 16 different 802.15.4 channels from 2.405 to 2.480 gigahertz. Each dot is 15 minutes worth of data on that channel, averaged over the whole network, of the reliability. And so, when I've got a long straight bar in here, that's 100% reliability. And you can see things drop down. And in some places, on some channels, they get really low. Over the whole network, at that particular time, it looks like maybe no packets were getting through on that particular channel. Was that Wi-Fi interference? Well, probably not. These are the Wi-Fi channels. They cover groups of 4 of these guys. And there doesn't seem to be a, well, there's a little correlation in there, but if it killed these two channels, why didn't it kill that one? So this is really probably multipath interference. It may be cordless phones and other things, but we didn't detect that. We have ways of detecting that. So it's really just the nasty nature of RF. You create a path, or you put nodes in fixed places, and they can talk for a while, and then they stop talking, and you don't know why. And it's because somebody moved a chair somewhere. And you've experienced this with your cell phones. You've experienced this with your Wi-Fi and your laptop. Can you hear me now? Oh, no. How about now? Oh, yeah, okay, that's good. Thanks. It's just the way RF works. So, yeah, so that's averaged over the whole network with the Wi-Fi bands over there. This is for a particular path, right? So this isn't averaged anymore. This is Mode 26 talking to Mode 17 now. And the good news is that when things look clear, they look clear for a long, long time. They're really nice, 100% reliability in there. But unfortunately, when things go bad, this is pretty clearly narrowband interference right there. There's 3 or 4 days in there where I'm getting essentially 0% of my packets through on this particular channel. And the problem is that if I'm building a single channel network, I get to look for a period of a minute or an hour or a day or something at the beginning when I'm building it, and say, well, this channel looks good. I'll pick this one, and I'll build my network. And this is what Zigbee does. The coordinator says, let's build a network on channel 12. And then everybody hears them and says, OK, we'll build one on channel 12. OK, we got it. And it just percolates out. And then at some point, crash. It goes away. So the big advance in Zigbee Pro over Zigbee 2006 is the way they're going to fix this is after you've lost connection with your network, you tell the network to switch to a different channel. Really, that's the solution they came up with. So you can't, you can rebuild a network, but you've got to rebuild the entire thing. You don't know you can't talk to anybody anymore. So anyway, here's a really bad channel. And this is probably the worst one in the network. And then you can see there's some interesting stuff going on in here. There's clear periodicity now for days, right? Monday, Tuesday, Wednesday, Thursday, Friday. And weeks, right? You can see the chunks of weeks, the bands of Monday, Tuesday, Wednesday, Thursday, Friday through there. And then the weekends tend to be clearer. Not always, though. You can find channels that get better during weekdays at the same times that others are getting worse. I have no way of explaining this. This is just what it is. And I think I can release this data set to people if they want to play around with it. So this is one where if you guessed right, if you happen to pick this particular channel, which is dead center in the middle of a Wi-Fi channel, you would have had a great, this particular connection between 24 and 17 would have worked just fine. So if we look at some more detail on this particular network, so again now looking at what's the average stability over all these different channels, over all the things in the network, you look at it and say, oh, about 90%. That looks pretty good. I can pick any one I want, right? Any of these channels should be fine. Doesn't matter which one I build on. But it's because you're missing the granularity when you look at that average. Again, looking at path stability versus, or by path now, you find that the vast majority of your paths are very stable. And it's just a handful of them that give you trouble. So maybe the answer is, I just only use these paths and I just ignore those other paths down there. Well, unfortunately, that doesn't work either. So I can look at cumulative distribution function now. So if I'm ranking my let's see, basically I'm looking at the cumulative distribution of stability from 0 to 100% and sorting it by good paths, bad paths, and medium paths. What I find is that on bad paths, ones that have an average of 50%, between 40 and 60% stability. So half of my packets are getting lost on these things. It's sort of, more or less uniformly distributed. Things are going to be bad. But what I find is that even on good paths, right, even on ones where my average is between 80 to 100%, there's a long tail down here where it doesn't go to 0. So even good paths go away sometimes. And that's the thing that makes reliability hard if you have time deadlines. If I've got to get stuff there within the next 60 seconds, otherwise it's not useful to you, or in the next 6 seconds or whatever it is, and I have a great path that all of a sudden goes away, now I've got to figure out, oh shoot, let's try, how about this other channel on this link, or try that path. That's why you've got to build in all this diversity to make sure that you get that. And there's more, it's not spatially correlated. You can look at, that the three different colors of arrows show you the different paths, and then versus channel, how they worked. And you can see, well, red and green come from the same place, not a whole lot of correlation. Green and blue have the same moat in common, definitely not a whole lot of correlation. How about if we look, at this particular channel, channel 5, it looks like they're all about the same. But then you break it out in time and you see, they're not the same. Even though they look like maybe there's some correlation there. So it's just trying to emphasize for you, if you're working in this field, you need to be looking at data like this in order to make reliable networks out of a really nasty, unreliable RF channel. So, in that one, more PR. And now, 2 years later, we're not at 5 nines, we're at 5.5 nines reliability. So, and power consumption, looking at different nodes in this network, some of them are very busy, some of them are not. What is the current consumption? So this is what's publicly available from Dust right now. It's based on a TI MSP 430 microprocessor and a ChipCon 2420. And using this TSMP protocol, what the current consumption is from a very lightly used leaf node that is just sending one packet every 40 seconds, 30 seconds, something, maybe 60 seconds, I'm not sure. Something with a couple of children, or could have children, does have children, and has a bunch of children. This guy has, I think, 6 children and 2 parents, and is the most heavily used router in the network. He's burning 208 microamps and would live for 1.6 years on, I think that's on a AA lithium battery. I can't remember what battery we're using. And then the next generation, which we're just starting to ship to some of our customers now, is the 2140, and that drops the power consumption dramatically. So even this fairly heavily used router is running at 46 microamps, so you can get years and years of lifetime off of a good-sized battery with these things. So, and it doesn't just work in printing presses. 2 years ago, we also did this deployment at, in a oil refinery, and similar success. The neat thing about this one was, we had people install these devices who didn't know anything about wireless. They knew about oil refineries, and they put them in the way they normally put sensors in, real sensors that are sensing pressure, temperature, flow, and things like that, and everything worked great. And it's kind of interesting, if you imagine moats buried inside of here, right, communicating to other moats buried inside of here, there's no line of sight. All this metal looks like a gigantic hall of mirrors. And you really can't predict who's going to be able to communicate with whom. And so what you find is that you get some respectable stretches in here. There's many links in this network that are 200 meters. There's one, I think, that's 300 meters long. And yet there are other ones where, you can find stuff in here where, this guy's trying to talk to his neighbor next to him, and he sends something out 200 meters away and then gets it back, and then that guy forwards it over another 200-meter path. So really tough to predict. And that's why it's so hard to do the traditional star-connected network, right? Whether it's a cell network or a Wi-Fi. I put in a Wi-Fi access point, and everybody has to talk to it. Just not going to work in this environment. We have lots and lots of nodes that can bounce around with each other and be, continuously looking at the RF environment and figuring out what that should look like. That you can get to work. So these are the barriers to adoption. We nailed the reliability thing. The standards are coming. I don't have time to talk to you about that, but wireless HART is the industrial automation standard for wired sensors today, and the wireless version of that, we wrote the first draft of the standard, and it was modified and then voted on and ratified in September of this year, so now that standard is out there. SP100 is coming, IETF and IEEE are following. They're trying to basically adopt what we're doing for industrial automation because we're finally getting traction. Stuff just works, which is really, really satisfying. Good power consumption. As long as you can get 5 to 10 years of battery life, you hit most applications. And at Dust, one of the things that was really important is we sell complete networks. We don't let people write code on our moats. If you want to develop an application, you take one of our moats and you put a microprocessor next to it. You get to pick that processor and your development environment and everything else, and you just send us packets over a serial port. And so bad news is you have to buy a microprocessor. The good news is the network works, and you don't have to worry. Your software developers, or you as the poor person who has to write the application for your PhD dissertation, doesn't have to be mucking around with this funky operating system and environment, real-time delay-sensitive computing environment to get your network to work. So I said I'd show some applications. So industrial automation is where things are really taking off. So oil and gas production and pipelines and refineries, paper mills, chemical processing, stuff like that. A lot of companies have announced wireless HART products in this area. And this is the sort of thing these people are making. So Emerson was the real leader. This is their smart wireless starter kit that they've been shipping for a year now. That's got dust motes in it. You can see the little antennas on there. So these things have MEMS sensors inside of them that are, a $1 sensor, maybe a $10 sensor, but they sell for $1,000. And one of the reasons that they sell for $1,000, it takes a lot to produce these things, but it's because the average installation cost for them is $10,000. Because they run literally, on average, like a kilometer of conduit to get the signal out of this thing back to where it needs to go. It's incredibly expensive. So they haven't had a whole lot of pressure to reduce the cost because it didn't matter. The salesman goes in and says, hey, I've got one for $800 this time instead of $1,000. I don't care. I'm going to spend $10,000 installing it. What do I care whether it's $1,000 or $800? So this is why this industry is so excited about it. Now all the people who sell sensors think, boy, if this cost of $10,000 that they used to put into their budget for installation goes down to less than $1,000, maybe they'll keep the budgets the same size and we'll be able to sell 10 times as many sensors. And so that's what got them excited. And there's about 3 million of these sold per year. So, and it's not just those guys. This was a demo we did a little over a year ago with 11 different manufacturers in there. Bitter enemies, Emerson and Honeywell, both have their pressure transducers talking to other competitors' boxes, all using this wireless HART standard. They've all got Dust's TSMP stuff inside of them. So
this is your version of interrupt.
Yeah. Yeah. So with no competitors, that's the that's the nice thing about it. So, and this is, this is from Emerson end customer, people installing them. They're terrified of wireless. They like to think of wireless as if it were just invisible conduit. And so that's what we try to make them think. So they install it just like a wired device, and the data comes back, and they're happy, and they can imagine whatever they want to figure out how the data gets back. And it plugs right into the existing data systems that they're used to having in their plants. It just they don't have any way to tell from this console which of these are wired and which of them are wireless, which is perfect. That's exactly what you want. More real-world problems, right? You put up a solar-powered moat, and they spray paint it. Vibration monitoring, so this is more Emerson stuff. Plug this stuff onto motors and do predictive maintenance. So sending back time series data from vibration systems. These guys were pressure, temperature, flow, and tank level. They actually use a radar, a 2.4 gigahertz radar for tank level. So already identifying things. This is sort of a neat one. Bechtel went out to this new facility in Equatorial Guinea on an island out there, and they put these sensors, these wireless sensors in just to help them commission the place. So Bechtel has hired, after you build this multi-billion-dollar facility, the Bechtel team comes in and makes sure that it's all hooked up right, that all the arrows that were in the model are actually the directions that things flow in the actual facility. And so there's wireless Emerson sensor node sitting out there. So that deployment worked great. And then they pull them all out again after a couple of weeks. And so you can imagine for them, the cost of installation of this stuff is really painful. Right? So that's why wireless makes such a big difference to them. More kind of completely different application space. This is another Berkeley startup, Streetline Networks, started by Berkeley MBA Todd Dykstra, co-founder of Dust with me, and Mark Noralski, who's a BSAC PhD. So what they're doing, if you drive around and you look at those spots in San Francisco, drive around the streets there, you will see these little lane markers that are glued down next to the cars instead of being glued down in the middle of the street. And it turns out that those guys are checking to see when cars pull in and out and whether there's a car sitting in that space. And so there's a couple of applications of this. One of them, the fun one, is that if you know the right password right now, you can use your web-enabled cell phone and find the closest open parking space to your favorite restaurant. The city of San Francisco is more interested in determining the difference between the meter revenue and ticket revenue that they should have gotten and the meter and ticket revenue that they actually got, and making sure that they close that gap. So this is paid for by the city trying to increase the revenue. And so you can sort of think of this as as like Pac-Man, right? When these guys turn gold, that means that there's an opportunity to write a ticket there. And so they send the meter maids down the ticket-heavy streets and pick up all the gold. Big revenue. In 2002, City of Berkeley got $7 million in parking ticket revenue, and that goes into the general fund. So if you're a city council person, you think this is pretty cool. It's money you can spend on your cronies. Cliff Federspiel, another Berkeley startup, worked in the Center for the Built Environment and is using moats to improve simultaneously occupant comfort and energy consumption in buildings. And without changing the control, the actuation input. So you still got fans and valves and things like that, whatever you've got existing. If you just add more sensors and intelligent control, you can reduce energy consumption and increase occupant comfort. And so this is a big deal for him, and he's getting some traction on that. Couple ones that did not take off. So this is a building maintenance deployment that we did years ago, and for political reasons, this one got killed. Another one, monitoring grocery stores, another good application for energy consumption reduction. This one, for political reasons, also got killed inside of Honeywell. This was sort of a fun picture in that this is a licensed electrician who was brought in to do this. He's screwing in the power sensor right there. There's the cabinet. By Honeywell's calculations, it is still far cheaper to put in a wireless battery-powered sensor system than it is to have this guy install another circuit in here and tap into the 110. Perimeter security, so this is work with SAIC and Dust. So SAIC is a defense contractor, well, and public contracts in San Diego area. So they made a bunch of boxes that look like this. This particular one has a magnetometer in it. There's one with a seismometer for detecting footsteps. There's passive infrared, a microphone, and a camera. And here's one where so there's a trail out there by SAIC that they deployed these things along, and so there's a bunch of, so the triangles here are passive IR, the circles are the geophones or the seismometers, and then the star is the camera. And on the horizontal axis is time. And so what they do is each one of the sensors detects when something goes by it and puts a timestamp on that and sends it into the network. And their software fits a line to that and figures out what's going along there, when it's going to go by the camera, cues the camera to take a picture at the appropriate time, and then records all this stuff as an event that happened in the log. And you can watch it in real time, or you can go in the next day and see what happened. You can click on an event and see, here's the picture that the camera took at that time. Or you can go in and you can look, here's the signal from the geophone, or you can download the time series from the microphone and listen to it yourself and see whether it was valid. And the neat thing about this, they packaged this thing up and gave it, put it in a suitcase and gave it to these 19-year-old Marines at the Chocolate Mountain Gunnery Range, where they have a real problem with people coming across the border from Mexico to get to I-10. And unfortunately, they walk right through a live fire gunnery range. And so these young Marines with no training took a suitcase out and put in these two networks, and it just worked. And they had only what they thought was only one false positive or false negative. They weren't sure, because every time they saw something come in on the south side, it always came out on the north side, and vice versa, except one of them. And then they went and looked, and they found that actually someone had abandoned a pickup truck in the middle of the base. And so they actually was perfectly successful. Get about 3 years of battery life out of these things, the sensor and the network working simultaneously. And unfortunately, they're getting zero traction, again, for strange political reasons. DARPA thinks that they funded this stuff and that they're done. So it all worked, and they don't need to put any more money into it. The Defense Department thinks that it's not ready for prime time yet, because all the demos that the academics did, we brought in a bunch of generals to look at these things, and they looked at fabulous academic demos, wonderful things that happened, came out of the NEST work at Berkeley. But bring a 4-star general in to look at it. Okay. So we're caught in this no man's land. And even though this escalated through the Marine Corps to a 3-star general who's the head of Marine Forces Pacific, wrote a letter to Tony Tether, the director of DARPA, said, we need this in Iraq right now. There are kids dying because we don't have this stuff over there. And Tony told him, buzz off. It's not my problem. So very frustrating, but that's the way it goes. So finishing up, this is where we were in 2001. I was predicting single chip motes. We built one in 2003, set some records for low power radios. So that, after doing the software at Dust, we moved into the hardware side, or actually had that program going all the time at the university. So Al Molnar did the 900 megahertz radio. Ben Cook did the 2.4 gigahertz radio. Both of those guys consulted at Dust early on. And so where we ended up, this is the mote that we had back in '99 that Seth Holler made. And I tried to, I don't know if the euro is bigger or smaller than a penny, but this is where we are now. So this is a mote. It requires a battery and an antenna, so it's not quite fair, right? So remove the antenna and the battery from this picture, and then it's a fairer comparison. But it's also different in that this thing comes complete with all the networking that you need to do ultra low power, reliable, secure communication. And it's kind of a neat package. It's got our custom ASIC in it. It's got a power amplifier, balun and matching circuitry, 2 crystals, and everything else. It's really a complete mote in a SoC package. And the performance, this is radio receiver performance in milliamps versus data rate. These are the chips that everybody in the industry has been using. Oops. That's what we can get today, 10 years of lifetime off of with a D-cell battery. This is my student Al Molnar's 900 megahertz radio, roughly 25 times lower current than the comparable commercial one. Jan Rabai had a very nice MEMS radio. Brian Otis, the student who did that work. My student Ben Cook did a 300 microwatt radio, literally 100 times lower power than the comparable thing that's on the market. Meanwhile, commercially, Atmel came out with a pretty nice radio, probably the best done radio out there to date. This is Atmel one at 16 milliamps. Ember, our former competitor, is literally off scale. Can't put it on the same chart. Freescale, 4th rev of their silicon, came out, 35 milliamps in receive, and Dust just started talking about the numbers on this one. So we're at 6 milliamps now and going down. That radio was designed by another mechanical engineer, as it turns out, a student of Bernard Bozer's named Mark Lemkin, who's working at Dust. So where are we headed? Next generation, all the things that we had before, the microprocessor, the memory, the radio, the sensor interface, adding in hardware for security, location is really the next key thing, and then starting to get rid of all these components. And it turns out that's what there's some neat research on getting rid of everything, bringing on the crystal, bringing on the antenna, and even bringing on the power supply, making the mote solar powered. So literally, the chip itself, with just sitting there on the tabletop, is scavenging light from the environment, converting it into electricity, running its radio, transmitting with an on-chip antenna, and communicating with its friends. So 0 external components. And the time of flight is research that Stephen Lanzasera is doing now, so that we can get 1 meter location accuracy in 3D indoors. That's coming soon. So, final slide. 10 years later, we finally have a real market. Nobody knew it was going to be industrial automation, and turned out that reliability and low power were critical. It's unfortunate that the university impact is really just the vision and warm bodies, and virtually nothing that we've done in the university has had an impact on any of the standards or anything else, and that's an unfortunate fact that we could talk about offline. The future is all of the applications that everybody has been talking about all these years. We now have the technology to deliver to these things at low cost and reliable and secure, which are all the things people need. So with that, I will thank you for your attention.
Let's have a few questions, and there's microphones to pass around. Let me walk back here. Oh, sorry.
If you decrease the security or encryption standards, how does it affect reliability and other things?
So the reliability and security are not directly tied to each other. If you assume that you don't have anybody trying to attack your network, then turning security off has no impact on reliability. But at the same time, so that's the real answer. I have so far, we've been asked many times to turn off security. We don't want security, it's too complicated, blah, blah, blah. I've resisted that every single time. I don't ever want to ship a network that ends up being installed someplace that matters, that somebody ends up cracking. Because that, it's not going to take many of those, like one, to really set the industry back. You know, and these guys, it's interesting. One of the guys from Shell recently, who's on the security group in SP100 with me, defining the next standard, said, you know, the kind of crypto that we use for internet banking, right? People have millions or billions of dollars on the line with this. Is that good enough? Well, the reality is that these guys write off roughly 1% per year in terms of fraud. And you know, so this guy from Shell says, how many of you are willing to write off 1% per year of people breaking into your wireless sensor network that controls your, you know, chemical process facility, your natural gas processing facility? You know, imagine Bhopal, right? 0, right? So that's and I don't ever want to be in that situation. So there are issues with exporting to China. We have to give them the keys, but separate discussion.
Another quick question.
Sure you want to take a question?
Chris, I have a question about the power consumption of the new dust mode.
Uh-huh.
So you said the average power consumption is around 6 milliamps. So does that consider the duty cycle, or is it the state at the transmission or the receiving state?
6 milliamps is the receiver current when the receiver is running. And so the receiver runs at, you know, typically a 0.1% duty cycle if you're a leaf node or less. And so that ends up being 6 microamps. So if you're a router and you're forwarding a packet every second or two, then it's running at 1%, so it's, you know, 60 microamps or something.
So the reduction in the power consumption is due to the integration of the algorithm into a single chip, or is it an achievement in terms of the radio hub?
So the algorithms are most important, right? The algorithm doing TSMP lets us go from, you know, the radios being on all the time in order to forward down to radio duty cycles of, you know, 1% or even a 0.1% to keep the network synchronized. That's sort of where we bottom out. So that factor of 100 or 1,000 due to the algorithm, and then another factor of 10 roughly due to intelligent chip design. And there's probably a factor of 5 due to the chip right now. There's another factor of 10 on the table that we will, as a community or as an industry, work our way down over the next several years.
One last question in the back, because we've. Oh, and then anybody else should come and chat afterwards.
I have a quick question on the the penetration through barriers. How the modes have advanced over the course of time in the last 5 years with respect to penetration through barriers, especially with some of the technologies that we are studying here at the lab, which we think the barriers are one reason why these technologies are not being adopted faster than they should have been, and that piggybacks on the reliability question. So what do you...
and when you say penetration through barriers, you mean walls?
Steel walls, concrete mortar.
Right, so this is all about all those curves that I was showing you before, right? I mean, that is we quote a range in our networks of 100 meters indoors. We're using with the same radios that everybody else is using, right? It's not magic. It's the fact that we keep hopping over all the channels. We have path diversity and everything else. So it's, this is that is why I had the whole middle of the talk about that, because it's that is how you solve that problem. You don't, if you can't go through a wall at a particular channel, then you try a different channel and magically you can. Or you try a different moat, or you try it again a little bit later and you can. And so we have done, I don't know, is it 1,000 deployments yet? I mean, we've got a long list of customers that are putting these things out there all over the planet, right? And we have never had somebody come back and say, we can't get this thing to work and to get the range that you guys are quoting. So
last question from Professor Goldberg here.
Chris, this is great work. If you could you just say a quick word about optical signaling?
Love optical. It's where I started. If you have line of sight, you can do optical communication for much lower power than you can do RF communication. But it's that line of sight thing that gets in the way of virtually all the applications that people are interested in. Not all, but virtually all.
Very good. And thank you very much, everybody, for staying. And we'll see you next week.